When you look up at the sky, you probably see fluffy, weightless cotton balls. They drift lazily, like ships on a blue ocean, seemingly without a care in the world. But what if I told you that a single, average-sized cumulus cloud, one of those classic puffy ones, can weigh as much as 100 elephants? That's over 1 million pounds of water, or about 300 cars, hanging right over your head. So, what's holding it all up? The answer is a wild, constant battle between immense weight and powerful atmospheric science. It's a story that involves microscopic droplets, invisible elevators of air, and a delicate dance of density that all happens thousands of feet above us. First, let's get one thing straight. A cloud isn't a solid object. It's not a giant marshmallow or a piece of cotton. If you could fly through a cloud, you wouldn't hit some fluffy wall. You'd just fly through a patch of dense, moist air. In fact, if you've ever walked through thick fog, congratulations. You've walked through a cloud that formed at ground level. A cloud is really just an enormous collection of countless microscopic liquid water droplets, or, if it's cold enough, tiny ice crystals. These droplets are so small and spread so far apart that the cloud isn't one single heavy object. It's more like a fine mist, stretched out over a huge area. Researchers estimate that the water density in a typical cumulus cloud can be around 0.5 gram per cubic meter. To picture this, imagine a box big enough for you and a friend to sit in. The total amount of water in that box would only be about the size of a marble. That's not much at all. The only reason a cloud weighs 1 million pounds is because it's gigantic, often 1 kilometer wide and 1 kilometer tall. So, the weight isn't concentrated. It's distributed across an immense volume. This wide distribution is the first major clue to our puzzle. Now let's zoom in on one of those individual water droplets, because this is where the magic really starts. The average cloud droplet is only about 20 micrometers in diameter. That's smaller than the width of a human hair. Because these droplets are so minuscule and lightweight, gravity just doesn't have a very strong pull on them. This brings us to a key concept in physics: terminal velocity. It's the constant speed a falling object hits when air resistance perfectly balances out the force of gravity. Think about dropping a bowling ball versus a feather. The bowling ball has a high terminal velocity and plummets. The feather, with all its air resistance, has a super low terminal velocity and just kind of drifts down. A cloud droplet is like an ultra-lightweight feather. Its terminal velocity is incredibly slow, often just a few hundred feet per hour. Since clouds float thousands of feet up, a fall rate this slow is practically unnoticeable from the ground. The droplets are technically falling, but so slowly that they look like they're suspended. They're just tracing the movement of the air around them. This ridiculously slow descent is the first force working against gravity, but it's not strong enough on its own to keep a 1 million-pound cloud afloat forever. It needs a partner. That partner is the single most important factor keeping clouds in the sky: rising air, or what scientists call updrafts. It all starts with the sun. When the sun shines on the earth, it doesn't heat the air directly. It heats the ground, the oceans, the land. And this warm ground then heats the layer of air right above it. Here's a fundamental rule of nature. Warm air is less dense than cold air. As air molecules heat up, they get energized, spread out, and take up more space. Because this warm, expanded air is lighter than the cooler, denser air around it, it starts to rise. This process is called convection, and it works exactly like a hot air balloon. A hot air balloon floats because the air inside is heated, making it less dense than the outside air, which creates a buoyant force that lifts it up. The same thing is happening all over our planet. Columns of warm, moist air are constantly rising from the surface, creating invisible elevators. As these elevators of air ascend, they push up on the billions of tiny cloud droplets. The force of this upward-moving air is stronger than the slow terminal velocity pulling the droplets down. So the droplets are in a constant state of push and pull. They are slowly falling, but they are being continuously shoved back up by the powerful updrafts from below. This creates a dynamic equilibrium where the droplets are held aloft, and the cloud appears to float because its tiny parts are falling slower than the air is rising. We've covered the tiny droplets and the powerful updrafts, but there's one more piece to the puzzle: the density of the cloud as a whole. A cloud isn't just a collection of water droplets, it's a huge parcel of warm, moist air that contains those droplets. And just like that hot air balloon, this entire parcel of air is less dense than the cooler, drier air surrounding it. Think of it like a massive ship on the ocean. The ship is made of steel, which is way denser than water. So why does it float? Because its shape displaces a huge amount of water, and its total density, including all the air inside its hull, is less than the water's density. A cloud is the same. The entire mass of warm, moist air and its suspended droplets is, as a whole, less dense than the cooler, drier air around it. This creates buoyancy, an upward force that helps keep the whole system afloat, like an invisible cushion of air supporting it from below. There's even another fascinating feedback loop at play. The process of water vapor condensing into liquid droplets actually releases a small amount of heat, called latent heat. This released heat helps keep the air inside the cloud just a tiny bit warmer than the surrounding air, which enhances its buoyancy and strengthens the updrafts that support it. So with all these forces working to keep clouds up, why don't they just float forever? What finally makes a cloud release its water as rain? The answer is that the droplets finally grow big enough to win their fight against the updrafts. Inside the turbulent, swirling environment of a cloud, those billions of tiny droplets are constantly bumping into each other. Through a process called coalescence, they merge and combine, forming larger and heavier drops. As a droplet grows, its weight increases much faster than its surface area. Eventually, some of these droplets get so large and heavy that their terminal velocity becomes too great for the updrafts to support them. Gravity's pull overwhelms the upward push. Once a droplet is heavy enough, it begins its journey to the ground. As it falls, it collides with and gobbles up even more small droplets on its way down, growing larger still. When millions of these heavy drops fall from the cloud, we experience it as rain. In colder conditions, a similar process happens with ice crystals, leading to snow or hail. The cloud itself doesn't fall. It just releases the parts of itself that became too heavy to float. Ultimately, clouds float not because they're weightless, but because of a perfect and powerful combination of factors. First, they're made of water droplets, so microscopic that gravity has a weak grip on them. Second, they're constantly held up by powerful updrafts of warm, rising air that push the droplets up faster than they can fall. And third, the entire cloud system, a massive parcel of warm, moist air, is less dense than the cooler air around it, letting it float like a great ship on the atmospheric sea. It's a delicate dance between the downward pull of immense weight and the relentless upward push of atmospheric science. So next time you see a cloud drifting overhead, remember the 100 elephants it might be holding, and the incredible invisible forces that keep them hanging in the sky. So the next time you see a seemingly peaceful cloud, you'll know about the incredible, invisible battle taking place inside it. It's a story of physics and forces that turns our sky into a dynamic, ever-changing canvas. If you found this explanation fascinating and want to uncover the science behind more of our everyday world, make sure to hit that subscribe button and ring the notification bell. And let us know in the comments. What other everyday phenomena have you always wondered about?